Hi, this is Professor Fernandez. In this video, we are going to work through example 2.7 from my book, Calculus Simplified. So this example says, use theorem 2.3 to determine the smallest n value, guaranteeing that a left-hand Riemann sum approximation to this integral is accurate to within 0.01. Okay, so I'm going to zoom in here because we need to use theorem 2.3, which I've pasted in here. If you'd like to pause the video now and just take a look at this theorem to sort of read what it says, that'd be a good idea. But I'm just going to go ahead and use it, assume that you've either read through the theorem or paused the video. So let's go back and then see what we really are asked to do. So first of all, I have an integral. This is integral from 1 to 2, 1 over x dx. And if I'm going to use any theorem, including this one, I have to verify the hypotheses for the theorem. So I'm going to go in here and start reading this little paragraph here. And just by way of orientation, right here is the then in the theorem statement. So all of this stuff over here is part of the conclusion of the theorem. Everything that precedes the then, all of these things over here are hypotheses. That's what I have to verify in order for me to use the theorem. So let's read through these hypotheses and again verify them in this specific context. So let f be integrable on AB. This just tells me, asks me to verify that if I look at this function, little f is this function 1 over x, the integrand. And if I plot this on the interval that I'm looking at right here, do I have a finite area between the curve and the x-axis? The answer is yes, I do. In other words, this theorem only applies for that setting. You can imagine why, right? If you have a function that maybe has an infinite area, like 1 over x, including the interval, the x value 0 here. If you have an infinite area over here, then you're going to have a problem trying to use a Riemann sum to estimate that integral, because the integral will have infinities in it. So we verified the first part of the theorem. Up next, let L sub n, R sub n denote its left and right hand equipartition Riemann sums. Okay, don't have to verify anything there. Suppose further, another verify, that the integrand is either non-decreasing or non-increasing. So in our case, the function that I've drawn, right, 1 over x, our little f here, is decreasing. So indeed, that function satisfies these criteria, right? So it is not increasing. It is indeed decreasing. So it satisfies that one. Okay, so I verified all the hypotheses here. So now I'm going to go back and use the theorem. So what does the theorem say? Well, the theorem says the error, ELN or ERN, the errors are at most these quantities in absolute values. Okay, so what do I need to do to actually answer my question? I need to find the smallest n value, guaranteeing that a left-hand Riemann sum, left-hand, so I'm going to use this equation over here. Approximation to this integral is accurate to within 0.01. So here's how you do these types of problems. First of all, we'll go back to our integral and we'll just identify certain things. This is the integrand. This is little f of x. This is number 1 is the a value. This number 2 is the b value. So, and I know I'm using this formula because I'm looking for the left-hand Riemann sum. So then I'm going to go in here and sort of write down everything that I know. I don't know n, right? I don't know this little n. That's part of what I'm supposed to find, smallest n value. But I do know a and b, right? I just found b, I just found a. So over here, b minus a, b is 2, a is 1. There we go. And then absolute value, I'll just plug in here what b is, 2 f of b minus f of a. There we go. And then I'll leave the n as is. Okay, so then I'll simplify a few things, right? I do know my function. My function is f of x is 1 over x. So when I go in here to find f of 2, this is 1 over 2. F of 1, this is 1 over 1. And now I'm going to calculate everything here. 2 minus 1, that's 1. Absolute value of 1/2 minus 1. 1/2 minus 1, and then divided by n. Okay, so in the absolute value, I just get 1/2 minus 1, that's negative 1/2. And absolute value of negative 1/2 is 1/2. And if I'm dividing 1/2 by n, that's the same as 1 divided by 2n. So now I have my written out ELN in absolute values. This again is the error in using the left-hand Riemann sum to approximate an integral. Okay, so I have that quantity. Now, my problem tells me that I want this error to be accurate to within 0.01. So what I want to say is this error that I've calculated here has to be less than or equal to 0.01. You can see that I'm now going to have to find the n value by solving this inequality. So let's do that over here. So I have 1 over 2n less than or equal to 0.01. This happens to be tenths hundredths, 1 over 100. So now I'm solving 1 over 2n less than or equal to that. I can take the reciprocal of both sides, 2n over 1. That changes the inequality sign, greater than or equal to 100 over 1. So I have 2n bigger than or equal to 100, divide by 2, and 100 over 2 is 50. So my conclusion is that so long as n is greater than or equal to 50, then everything else that we've shown over here tells me that 1 over 2n is less than or equal to 0.01. And 1 over 2n over here was exactly my ELN. So conclusion, if n is 50 or more, the error in using the left-hand Riemann sum to approximate this integral will be at most 0.01. So all I need are 50 or more rectangles, basically, to form my left-hand Riemann sum and ensure I get that level of accuracy. Okay, see you next time.